Hello students, today we learn the practicals from dynamics of machineries. The aim of practicals is to verify the relations of simple pendulums. So we know that in simple pendulums, the frequency of simple pendulums is depends on the length and it not depends on the mass attached with the string. So in these lectures we have to verify the relations of simple pendulum. Now, before we start our practicals, we have to just go for the theories, how to calculate the natural frequency of simple pendulums. So, as we know that in simple pendulums, there are the one strings and the one mass is attached at the end of the strings, and one end the string is fixed. So here small l is nothing but the length of the strings, and here the mass attached with the spring is nothing but the small m. So this is nothing but the simple pendulum system. Now to start oscillations, we have to give a small angular displacement as theta. You can see that here we give us a small angular displacement, that is theta. So our systems will start vibrating. So here if we give the small angular displacement theta, as we know that there are the opposite directions, the inertia torque will generate, and that is nothing but the I0 into theta double dot. And this force due to the mass m is nothing but the mg sin theta. So to calculate the frequency of simple pendulum systems, we have to take the moment about O points, and for the equilibrium positions, we have to consider the summations of moment about point O, that is equal to 0. So we have to take the moment about point O and we have to make it is equal to 0. So here the inertia force, that is inertia torque, that is equal to I0 theta double dot, and the force here, that is mg sin theta. So due to this force there are the moment is mg sin theta into small l, and that is equal to 0. So if we simplify our equations, we get 0 is equal to theta double dot plus mgl upon I0. Here instead of sin theta, we have to place the value of theta, because there are the small angular displacement, and for the small value of theta we have to consider sin theta is equal to theta. So this is our equations. Now we have to compare our equations with the simple harmonic motion equations, that is theta double dot plus omega n square theta is equal to 0. So if we compare, we get the omega n square, that is equal to mg small l upon I0. So we get omega n, that is the natural angular velocity for the simple pendulum system, that is equal to under root mg small l upon I0. If we place the value of I0, that is ml square, we get omega n, it is equal to under root of g upon l. So this is the angular velocities for the simple pendulum systems, and we know that frequency is omega n upon 2 pi. So Fn is equal to 1 upon 2 pi into under root g upon l, and time period is the inverse of the frequency. So we can write Tp, that is the time period, that is equal to 2 pi into under root l by g. So here you can see that the frequency is depends on the only length, small l. So that we have to prove by the practicals. So let's first consider the case 1. In case 1, we have to consider the mass m is equal to 60 grams. So here we consider it m is equal to 60 grams. That is the mass of bob, and a length of the string is considered as 62.5 centimeters. And here we have to consider the time for the 10 oscillations. So you can see that here the length, first of all we have to measure the length of the string, and that is equal to 60 centimeters, and also we have to consider the radius of pearl. So total length is 62.5 centimeters. Now we have to measure the time for the 10 oscillations. So here you can see that the time, here you can see that the time for the 10 oscillations is we get 16.03. Again we have to repeat the process. Here we have to give the small angular displacement, and then we have to measure the time for the 10 oscillations. So second times we get the readings. It is 15.54 second. Now third times small angular displacement is given, and we have to measure the time for the 10 oscillations. So we get the readings is 15.98 seconds. So we get the three readings or three observations for the 10 oscillations, that is 16.03 seconds, 15.54 seconds and 15.98 seconds. So here to calculate the frequency for the first case, we have to make the average of these three readings, and the average of these three readings is nothing but the 15.94 seconds. So here the number of oscillations is 10 and actual time periods we have to consider as 15.94, that is the average of these three readings. So frequency we get Fn is equal to 0.6273 Hertz practically. So now we have to consider the case 2. In case 2, we have to change the mass. M is equal to 25 grams. So in first case, there are the mass M is 60 grams. In case 2, there are the mass is 25 grams. And length of the strings we have to consider as same, that is 62.5 centimeters. And here also we have to follow the same process. We have to measure the time for the 10 oscillations. So you can check, first of all we have to measure the length of the strings by using the scale. So here it is 60 centimeters, and also we have to consider the radius of wall, so that is 2.5 centimeters. The total length of the string is considered as 62.5 centimeters. Now we have to given the small displacement, so systems will start vibrating, and then we have to measure the time for the 10 oscillations. So we get the time is 15.60 seconds. Same process we have to follow again. Second times we get reading 15.79 seconds. So we have to consider the three readings for better accuracies. So here in third times we get the result is 15.65 seconds. So here you can see this in our observations tables. There are the first reading is 15.60 seconds, second reading is 15.65 seconds, and third reading is 15.79 seconds. So we have to take the time period is nothing but the average of these three readings, and that is nothing but the 15.68 seconds. And we know that frequency Fn is equal to number of oscillations upon actual time period. So here oscillations we consider it 10, so we have to place value is 10, and the actual time period is 15.68 seconds. So we get frequency Fn is equal to 0.6377 Hertz practically. Now you can see that in case 1 what we get, the frequency in case 1 we get 0.6273 Hertz. So if you compare the case 1 frequency and case 2 frequency, you can see that the frequency is nearly same. So that means what? From the case 1 result and from case 2 result, we can conclude that the frequency of simple pendulums does not depend on the mass, because in case 1 and 2 there are the change in mass. Now we have to consider the case 3, and in case 3 we considered the same mass as we considered in the case 1, that is 60 grams, and length here we have to change, that is 32.5 centimeters. So let's first measure the length of the strings by using the scale, and that is equal to 32.5. So here the length of string is 30, and also we have to consider the radius of box, so that is equal to 32.5 centimeters. Then we have to measure the time for the 10 oscillations. Here we get the readings. Same process we have to follow, and we measure time for the 10 oscillations. We get third times, we get the result is 12.09 seconds. So here we have to measure the times for the 10 oscillations for the 3 times, and then we have to make the average of these 3 observations, and we have to place in our frequency equation. So if we place in our frequency equations, we get it is equal to 0.8438 hertz. So practically, if you compare a case 3 result with the case 1, so you can see that there are the change in frequency. In case 1, there are the 0.6273 hertz, and case 3, there are the 0.8438 hertz. So that means what? The both the case has a different frequency. So what is the change in case 1 and case 3? Changing length in case 1 and case 3. So that means what? The frequency of simple pendulums depends on the length of the spring. So in this way, we can validate the relations of simple pendulum systems. Thank you.